if you have attended the talks yesterday, you would have realized we are covering different areas of astronomy and astrophysics. There were talks on numerical simulations, 2 talks. Even they were on like very different topics, one on fluids, another one on radiation. And then we had 2 talks on data, different kind of data coming from the radio telescope. And we will continue this approach throughout today's lectures as well. So let us go to the first lecture today. So the first lecture will be by Professor Dipanjan Mukherjee of IUCAA. He's a faculty member at IUCAA, and his research interests, he's a theoretical astrophysicist who mainly works on, again, numerical simulations of fluids and magneto hydrodynamics. And today he will be concentrating on one aspect of his work, that is supermassive black holes and jets from there. And I hope you will enjoy and find it interesting and realize how HPC is important in such kind of problems. So yeah, I request all the participants to keep themselves muted to avoid any disturbances. And normally we will have the questions at the end, unless Dipanjan wants to take something in between. So I will leave it to Dipanjan. Dipanjan, please start.
Thanks, Sid, for the nice introduction. So again, just sharing my window. Please confirm if you can see my screen and full screen.
Yes, it's now on full screen. Yeah.
Thanks, Sid. So welcome everyone for this first lecture today. Today, my lecture would be slightly a slight departure from the previous ones, where the tone of the lectures are more pedagogical. I will be talking and the basics about the computation and applications. I would be talking about one of the applications that we do, so more about the results. But I will switch between the basics of fluids in the middle, where I highlight some of the schemes, then go back to some of the results to show you an overall picture of what we use this HPC to answer some of the cutting edge questions, at least from my in my field of interest, and how do we go about it. So the results that I'm going to present have been done using supercomputing facilities at different places in Australia as well as in Italy, where I was a postdoc. And it was done in collaboration with a large number of collaborators, like listed here, which comprise both from the people from the theoretical background, helping us understand the codes and develop new schemes, and also from the observational background. So this, to take forward this thing, when you produce realistic simulations, we also need strong inputs from the observing community to give us understanding of how the universe actually looks like when they observe through telescopes, and how from the theoretical side we can push the boundaries and try to match and recover some of the aspects to then tune our parameters and see which one works to describe what we see in reality. So without further ado, let me start by showing you this simulation. So before I start the movie, maybe I can start the movie itself right now. So this is a movie of an illustrious simulation. Now, this is a kind of simulation. It's called a N-body simulation. This is something that we did not talk about in this particular workshop, but hopefully in future ones we'll have more representation from this. What you're seeing here are all these individual points are actually galaxies. So this simulation is over a megaparsec or larger than that. And what you're seeing here is the galaxies and the gas associated with them collapsing and forming these filamentary structures just due to their interaction due to gravitational attraction. And then as the galaxies start to form, you can see they're starting to glow because they're starting to form stars. And you can see right around here, you can see that there will be a large explosion. It will start, there you can see. So what's happening here is that as the galaxies are gathering a lot of mass, they are channeling that inside the black holes, and the black holes become active. And then as the black holes become active, they have a lot of power, and I'll come to that more in the rest of the lecture. They throw out matter from these galaxies. So these are like explosive events. They are very powerful, and they can remove a lot of content from mass from the galaxies and redistribute it to the environments, where from again the gas can fall back in, and it's like a continuing cycle that takes place and keeps the galaxies in a steady path. So this is the topic of something that we are all interested in, which is how the supermassive black holes inside the galaxies regulate the growth of the galaxies. Now you can see after a certain phase, the galaxies have settled down into a steady phase where you can see there are some clusters of galaxy at different places, but you can also see they're aligned in the filaments. But they have that rapid activity has decreased to some extent. So if you look at from the cosmological point of view, we have the galaxies initially forming, and this is something that Girish also talked about yesterday, that as the galaxies form, they create mass and their activity starts to grow, and at about redshift of 2, we see a peak of the activity of the star formation processes. And then it slowly declines and we have a lull. And I just wanted to share this image on the top right corner. This is an actual observations of the distribution of galaxies arranged as a function of the redshift going backwards. And you can see that the distribution of galaxies is indeed observed filamentary, similar to what was seen earlier in the movie, for example, this snapshot. So this is a nice demonstration that this kind of simulations are pushing the boundaries and starting to recover the large-scale structure of the simulation. What is important to understand is these kind of simulations are extremely expensive and very complicated. There are a lot of different kinds of physics that are going in here. For example, there is just the basic forces of gravity. But as the matter falls inside, you have stars that are forming. So just from the theoretical point of view, we need to devise some schemes that can capture the physical process of formation of stars inside a computer. And then as the stars are forming, they also shoot out matter and then they heat up the gas. So not just the gravity, but we also have to simultaneously evolve the hydrodynamics of the system. And that is why this kind of simulations are very complicated and very time consuming. This particular simulation, if I'm not wrong, is almost like 20 million CPU hours. But this is, again, outdated now. This was, I think, about 7, 8 years ago. And the recent ones have gone beyond that. So what is important to understand here is we are constrained by resolution. So as you try to you evolve a large-scale box of the galaxy, you can't really resolve the small-scale structures. So the name of the game is how deeper you can go in your simulations by resolving smaller structures. As you start resolving smaller structures, you have to make less assumptions about the subgrid phenomena and then try to see what naturally occurs inside these grids. And this is what people are doing. So there are two ways to do it. Either you just zoom in one of these galaxies and do the simulation of that particular galaxy itself. So that is called a zoom in simulation. And that is something that our group, I'll just stop the movie here maybe. I'll just, let the movie run and stop it at this slide. Yeah, so that is called a zoom in simulation where you just focus on a single galaxy and not this large scale cosmological box that I'm showing over here. The other is you take this large scale box, but then you start keep on increasing the resolution and you will eventually hit a wall. So there are two approaches and there are two ways of pushing. So start from the small scale, go to larger scales, or go from large scales and come back to small scales. So two different approaches. So just to give a brief introduction to the basics of galaxy evolution, I'll try to keep the jargon about astronomy and astrophysics less in this talk, but there will be a bit some of it. So in case you're not from the background, my apologies, but I hope I'll make it clear enough that you'll be able to understand. So this sequence of evolution that I'm going to show you shows you how the galaxy growth takes place during its lifetime, starting from the early phase when the galaxies are small and just forming to late phase when they have accreted a lot of gas and they have formed a lot of stars, and what happens then. So what I'm showing here is a plot. It's called a galaxy color magnitude plot, quite well known for the astronomical community. On the x-axis, you have the stellar mass, and this is the log of the stellar mass. Just to give you some numbers, our typical galaxies that we see, for example, the spiral galaxies, the Milky Way, for example, they are of the order of 10^10 to 10^9 solar masses. But you have very large-scale galaxies as well, which are 10^11 solar masses, the right-hand end of this plot. So these are the low mass galaxies, and these are the right hand mass galaxies, and there is a break in between where there's a transition. I'll not talk about that break right now. What we are showing on the y-axis is a difference of the color of the galaxies, U minus R color, but you can say that this is a proxy of the star formation or the stellar age of the galaxies. So are the galaxies actively forming stars? Are there new stars in the galaxies? The newer the stars, the bluer it gets in the U minus R magnitude plane. And that is why they are forming a blue cloud. So initially, so maybe I can start the sequence now. So so initially, as the galaxies start forming, they typically have masses of 10 power 8, 10 power 9 solar masses. So they are then initially just growing and accreting mass from different places. The galaxies can also undergo mergers, where two galaxies merge together and then we form a new single galaxy with a larger mass. And then initially we have is all these galaxies accrete a lot of gas. They're actively forming stars because the gas, once it starts falling due to the gravitational attraction and self-gravity, it will contract and then form stars inside. So these galaxies are called are generally appear as a blue cloud because they have a lot of young stars, and young galaxies actually the emission that you actually observed with the optical telescope, they appear blue because of the young stars being formed because of the emission lines. Now, as the galaxies are progressing, it has been found that the star formation rate declines, and they pass through an intermediate zone called the green valley and then to a red sequence, or the red and dead galaxies as we call them. So similarly, if you just focus on this plot, this is again the evolution of the log of the stellar mass and the star formation rate. The galaxies nicely are found to be correlated on a line here. So starting as they are growing in mass, they increase in star formation rate, but as they reach the red sequence, the star formation rate declines, and they form a new population that is over here. So what is important to understand is how does the galaxy transition from a blue cloud to a red sequence? So what causes this galaxy to stop forming stars? Is it just because they have extinguished all the fuel of star formation, which is the gas? So there is no new accretion that is taking place, no new gas supply that is going inside the galaxy? Or is there some internal mechanism in the galaxy that after a certain age, something happens in the galaxy and then prevents the galaxy from forming stars? So this is an open question, and this is extremely important for this large galaxies of large masses, mass ranges of 10 power 11 solar mass, let's say. And I'll show you why. So this is again a plot of the distribution of galaxies for different masses. The black points show you the observed results of galaxies at different masses, and the colored lines are from two different simulations. You can first of all notice that there is a break in this plot. So there is some behavior over here, and then after 10 power 11, or actually it starts from slightly below 10.5. It starts going down rapidly. So this phase of this galaxies with larger mass, they are called massive galaxies. So in the earlier periods when people were doing large-scale simulations, they found that just considering outflows from the stars. So what happens when stars form or galaxies form? Just forget about the supermassive black hole for now. The stars will form and they have a finite lifetime. So after some time, the stars will explode into supernovae. And the supernovae also can eject out a lot of energy and momentum into the surrounding environment. And if you have clustered supernovae at different regions, they can throw out a lot of matter from the galaxy. So this is called effect of the stars or stellar feedback. So in the earlier phase of the simulations in the before 2000 and so, people were solely focusing on the effect of the stars alone and not considering the effect of the central supermassive black hole. What they found was their simulations were unable to reproduce the galaxy mass function beyond 10.10 solar mass. So this is the blue line, and you can see it strongly overpredicts the number of galaxies you should form. So what's happening as supernova feedback in these massive galaxies is not strong enough to throw out the gas or do something that prevents the galaxies from forming more stars or accreting more stars or accreting more gas. So then people devise that maybe something happens that activates the central supermassive black hole, and we all know that almost all galaxies, even the dwarf galaxies, have a central supermassive black hole at the nuclear regions. So something happens in these galaxies that prevents them from forming stars, and then when they put in some prescription such that the supermassive black hole can transfer energy to the surrounding gas and process the gas around it and the circumgalactic environment, they found a very nice match with the observed galaxy mass function. So the green line is a simulation that considers the effect of supermassive black holes, these large-scale explosions that I've shown you a few slides back, and that is what it shows. So the central supermassive black hole is an important ingredient in understanding the evolution of galaxies. And how does the supermassive black hole? So this kind of simulations, again, are very coarse in resolution, but this effect of the supermassive black hole goes to different scales. I'll just show you in the next slide. So how exactly does the supermassive black hole sitting right at the center of the galaxy at very small scales compared to the large scale of the length of the galaxy affect the galaxy as a whole is an open question. And that is something that we are trying to address through both observations and simulations. So this is an example. So as I said, the supermassive black hole is extremely small compared to the length scale of the galaxies. But the supermassive black holes can eject out matter in the forms of jets and winds. And this is a simulation of the jets being formed by the supermassive black hole at the center. You can see there was an accretion disk sort of feature where some matter is being channeled inside the black hole. And as the matter, so these contours are magnetic field lines. And as the matter starts to fall in, a part of it falls in, of course, and a part of it is ejected. So this is this is how the supermassive black hole can actually, cause jets and outflows from the central system. And these jets and winds can be extremely powerful. So for example, I'll show you more examples of jets from these systems. They can reach relativistic speeds of almost 0.99 C or Lorentz factors of gamma 5 or 10 in the central regions, even larger for some cases, as we see in VLBI studies. So it's not that black hole absorbs everything always. Due to several different mechanisms, I won't go into the details of it. There are two dominant mechanisms by which you can produce jets. One is called the Blandford-Znaeck, and other the Blandford-Payne mechanism. The Blandford-Znaeck is fundamentally a GR phenomena, and Blandford-Payne is because of the twisting of the magnetic field lines in the accretion disk. So due to these different mechanisms, the black hole can conspire with the gas around it to launch these outflows, and these outflows and jets are extremely strong and powerful. But just before I go more into these jets, I wanted to give you a brief idea about the scales that are involved. So the Schwarzschild radius of a 10.9 supermassive black hole is about 10 power minus 4 parsec. So the next region is where inside each region, so inside the central region of galaxies, we have a lot of clouds that are moving about. For example, this is called the broad line region. So these are typically of the order of 0.1 parsec or 0.01 parsec. Again, 2 orders of magnitude larger than this. So beyond this, then we have the normal clouds of the galaxy or the gas clouds moving about. So these are called the narrow line region, 100 to 300 parsecs. But the size of the galaxy itself can be about 10 kiloparsecs. So starting from 10 power minus 4 parsecs, you have to go to 10 kiloparsecs. But the supermassive black hole and these jets and the winds are powerful enough to reach such large scales, orders of magnitude compared to the size of the black hole itself. But they don't stop at that. We have galaxy clusters where several galaxies are sitting together when a central galaxy just goes off. And these jets can go up to 1 megaparsec as well. So they can heat up the entire cluster where several galaxies are affected by a jet being given out by the central region of a single galaxy. So these are really exotic phenomena. They're really powerful, and they can go to extremely large length scales, even though they are extremely tiny compared to the size of the galaxy itself. So there are two ways of, as I said, of driving these winds. One is called radiation pressure driven winds. These are called quasar winds, where you just shine radiation from the central region, and then radiation pressure pushes out the gas. And I'll not go into the details of this, of course, but then other one is called the relativistic jets. So for example, these are some few images of relativistic jets. So this is Cygnus A, this is Centaurus A. The galaxy here is just at the center for Cygnus A. This point that you see, that is the galaxy. And this jet is extremely large. So you can see by orders of magnitude larger than the size of the galaxy itself. So these are all observed in radio. The Centaurus A image is a multi-wavelength composite image, where you can see the gas dust lane of the galaxy. And then you see this jet coming out and then fizzling out. So these jets can go to large sizes, and they can affect the galaxies at different scales. And what we need to understand is this energy transfer from these relativistic jets. How does this happen, at what scales, and over what time scales? So I had listed a few questions. This is from a more technical slide, but I'm just going to briefly summarize our main questions that we want to address. So for our perspective, our group's work, what we are really interested in is how these jets launched by the supermassive black hole, they affect the gas inside the galaxy itself, so scales of a few kiloparsecs. And then the circumgalactic environment, again, scales of a few kiloparsecs before they grow up to large scale sizes of Cygnus A of this several hundreds of kiloparsecs. So we are really focused on the central region of the galaxy itself and how the jets affect the galaxy. And more importantly, there are several important questions that come in. For example, what is the nature of the energy transfer by these jets onto the galaxies? How do they induce more turbulence inside the system, churn up the gas and increase the velocity dispersion? And how does all of this affect the efficiency of the formation of stars, or how is the star formation rate affected in these galaxies? As I said earlier, one of the major questions driving this field of study was how can we understand the evolution of assembly of the stellar mass of the galaxies? And to understand the assembly of stellar mass of the galaxies, we need to understand how these jets or outflows affect the gas inside the galaxy or the gas in the circumgalactic environment. So we've been running several simulations. I'll come to that later. These are quite expensive simulations as well, because they are special relativistic simulations that also account for interaction of the jets with the ambient environment, and focusing on length scales of 10 to 20 kiloparsec. Now here I will slightly digress a bit to give you some basic fundamentals of the equations we are solving and the methods. Prateek already gave a very nice overview of the finite volume schemes that we are using. I'll just briefly skim through them and then go to some of the results. So what we are solving are the equations of relativistic hydrodynamics. For our purpose, we don't need to assume a varying metric because we are far away from the black hole. Although the initial simulation I've shown you, which shows the formation of the jet, that is a GR MHD simulations. For our case, we just assume a flat Minkowski kind of metric. So all these G terms sort of disappear. What we can derive, how the way to derive these equations is you take the full mass and the matter energy stress tensor and then apply the conservation laws. And you get this in this equation. Again, the derivations are there in some of the papers that have discussed the numerical techniques of these systems. So the basic variables we are solving for are, again, the basic fluid variables, density, pressure, magnetic field, but there are some caveats to them. The density and pressure, these are measured in the co-moving frame of the fluid, whereas the velocity and the magnetic field, these are measured in the lab frame or the observer frame. And this is the proper density, this is the relativistic momentum, and this is the expression of the relativistic energy density. And we, as Prateek said yesterday, we also need another equation to relate the thermodynamics of the system. For a hydrodynamic system, it's a simple P equals to rho by gamma minus 1. For a relativistic system, we have to also consider the rest mass term. The c square is 1 here because the c is the unit speed of light. Okay, so this is how we formulate the equations of relativistic hydrodynamics. And then we also have the relativistic Magneto Hydrodynamics. Again, I will not spend much time on this, but just wanted to show you this slide because I'll try to give you some applications of this at the end of the talk. But now you also have to take into account the electromagnetic forces and their stress tensor. So essentially, I'm not going into the derivation of this, but you can see for the derivations in these papers I've listed here. This talk will be on the web, so you can look up the references then. Essentially, Mignone 2009, Mignone 2019, a recent paper on resistive relativistic simulations, and the book by Anile in 1990. What I wanted to emphasize here, though, are the fact that we write these equations in the covariant form, where we express the electric field and the magnetic field as their covariant form, and then we can recast the equation in a way that looks very similar to the MHD equations. And the only assumption that goes in is that, and in the rest frame of the fluid or the co-moving frame, the electric field is 0, that is infinite conductivity. So this term will become 0. And so this is the, essentially some form of the electric co-vector, 4 vector, and this term becomes 0. If you just substitute this into the other equations, you'll get this full set of equations. So that is the only assumption we make. This is in contrast to general MHD, where we also have to manually neglect the displacement current. So again, I just wanted to show you the next slide, just a comparison of how the equations look like in the normal MHD, the non-relativistic form. And if I just transition between these two slides, you'll find that there are several things that are common here. For example, the way this tensor looks like, which is the momentum flux tensor, is very similar to the momentum flux tensor that looks over here. So there are many similarities, of course, but all the similarities are hidden by the fact that we have to deal with the covariant forms in the relativistic framework. So I'll not discuss too much of this because Pratik has already nicely shown all of these equations, which is the conservative framework of the equations, where we write them as a conservative equation here, time evolution plus the divergence of flux equals 0. And then this is the primitive form of the equations, and even the relativistic equations have a primitive form. Just wanted to highlight this difference because one of the main bottlenecks of the relativistic simulations is this transformation from the primitive variables, primitive meaning where you define the quantities in terms of more understandable quantities, density, pressure, velocity. Whereas in the conservative framework, you'll have to define them in terms of the momentum and other things. So this transition from the momentum to the velocity has to be done numerically for a relativistic simulation because of the appearance of the Lorentz factor, and that becomes nonlinear. And this is a major bottleneck and which slows the code down significantly, besides other things in the schemes. Since we're talking about magnetic fields, I also maybe wanted to highlight some of the tools we generally use to tackle this problem of the fact that the divergence B equals 0 is a notorious thing that we have to maintain. And again, Pratik briefly mentioned this, but I felt that I should highlight it a bit more just to highlight some of the schemes so that in case in future you are ever want to go into it, you can have a better understanding. And I'll also show some of the RMHG simulations later on. So one of the methods, so as I said, numerically assuring that divergence B equals 0 is extremely tedious and difficult, because if you just do not pay more attention to it, you will immediately generate magnetic monopoles in your system. Unless you're you're not evolving the magnetic fields, but you're just evolving the vector potential, then you're all fine, because the vector potential by definition will give you the divergence criterion. So if that is not the case, then if you are just evolving the magnetic fields themselves using the standard prescriptions, then we have to add other constraints to ensure this. One is this divergence cleaning, where we add an extra term to this equation over here. So we are solving this equation. Instead of divergence B equals 0, we add this equation here. And then this is and we add a gradient of psi term in the induction equation. So just a simple manipulation here, you just take a divergence on the top equation and the time derivative on the bottom equation, remove this divergence b and del t of divergence b terms that come here, you will end up with this equation. It's very trivial. This is a telegraph equation. Okay, so this is what this essentially does. If you just, for example, so by the way, this is the Laplacian operator. For once, if you just ignore this term, this is almost like a wave equation, which we are all familiar with. This telegraph equation, what it does, it takes the divergence of the monopoles and advects them to outside the domain of your computation at the fastest possible speed. This CH and CP, these are all the characteristic speeds of the simulation. So the characteristic speeds can be the Alpine speed, the magnetosonic fast speed, the sound speed, or the fluid flow velocities. So whatever is the fastest possible speed that is allowed in the system, and that which determines your time step criteria based on the Coulomb condition, you will advect the magnetic monopoles outside the box. But while you are advecting it, this is an important part of the scheme, you will also damp their strength. So as you can generate magnetic monopole in a certain location, but this telegraph equation ensures that you are advecting it away from the system, but you're also decreasing its strength. So you can read up more about the telegraph equation to understand its properties later on. But this is how the divergence B cleaning works. So this is like almost like you're cleaning the entire box of the monopoles, and that is why it's called divergence cleaning. It was first introduced by Dedna in 2002. And quite widely used in many of the standard schemes. But this scheme then assumes that you will have magnetic monopoles in certain locations in your system. So it is not completely perfect. It is just almost like applying a bandage to your system, but not really solving the root problem. The other more efficient or more accurate method is called the constraint transport, where instead of solving the induction equation in a derivative form, we solve it in the integral form. So what we do is we take a line integral of this and solve the evolution of the magnetic field by integrating over the electric field. Now to do this, what you have to do is you have to define the electric field of the EMF, as it's called in some papers, on the edges of the cells. And the magnetic fields are defined on the faces of the cells. So as you would remember from Pratik's talk yesterday, we define our quantities at the center of the cell. So these are called the cell-centered formalism. But the magnetic fields in this face-centered, so if you have gone through some courses in condensed matter physics and things like that, you'd know in the crystal structure, we also talk about face-centered structures. So this is something similar where your velocity, pressure, and magnetic and density are defined at the centers of the cell. But the magnetic field are staggered. They are half cell away from the definitions of the pressure that lie on the edges, on the surfaces of the cells. And the EMFs lie on the edges of the cell. So to get this point, you just do a loop over these exterior points in this way and perform the line integral and you get this. Since we are working in this framework, this by definition, because we are defining the magnetic field in terms of a curl, this by definition will preserve the fact that the divergence B is conserved or will be conserved to machine precision. So if you set up your initial magnetic field to have no divergences, that will be maintained. However, if you set up your initial magnetic field to have some sort of divergence, that magnetic monopole will also be maintained. So the bad thing about this scheme is it is very difficult to set up, because of this way we define the magnetic fields, but this is the more accurate method of doing it. So just wanted to highlight these two schemes that we use in MHD to ensure this divergence B criteria, because this is a big headache when we do actual simulations. So just going forward, the code that I mostly used for all my purposes is this code called Pluto, which we now in India we have a good developer base. This is primarily developed by Andrea Mignone from the University of Torino in Italy, but also contributed by several different groups, including Bhargav Vaidya and myself. So it's a versatile code which has been widely used for several different applications. I personally use it for simulations of relativistic Jets and Relativistic Hydrodynamics. And it's freely available and open source, and you can obtain it from here. And it works in the Godunov scheme for the finite volumes. I think I am running a bit short on time, so I'll just skip the next few slides where I had just to put them to recap the Godunov scheme. But as you will know from yesterday's lecture, the Godunov schemes are volume average schemes, and that's why they are conservative schemes. Are very good for conserving your conserved quantities, the energy and momentum. One good thing about these schemes is since they're not based on derivatives but volume integrals, they're very good in handling shocks. This is in sharp contrast to the finite difference schemes, where if you have a strong discontinuity in your system, it can cause strong spikes in the derivatives, and that can create errors. So to minimize them, then we have to introduce artificial viscosity to allow the evolution of shocks. But in Godunov schemes, we don't need to do any such further schemes because we already are dealing with discontinuities, as Pratik showed by solving the Riemann problem. So these are the formulation of Godunov scheme. I'll just skip through them, and this is a Riemann problem, and we don't have time to go through them because I wanted to show you some applications. So this is the flowchart of the schemes. So we initialize the data at t equals 0. Then we go through the reconstruction phase, where if I just go to the previous slide, we first find the values. So we define everything at the centers of the cell, unless of course there's a staggered magnetic field, but let's forget the staggered field for now. We define everything at the centers of the cell, but then we transport them to the cell edges, because the Riemann problem, as I had shown, or as Pratik had shown yesterday, is computed at the edges of the cell. And I can talk more about this if you're interested later in the Q&A section. So this is called the reconstruction step. There are several different schemes with different orders of accuracy for this, and Pratik already showed it. We have several different slope limiters to ensure that the reconstruction is done properly. After the reconstruction, we go to the Riemann solver. We solve these discontinuities at the cell edges and solve for the solution of the fluid quantities at the cell edges. And then we perform a time integration, which is essentially the step of the Godunov scheme. So we essentially perform this time integration. So we need to find the fluxes at the cell edges, and then we need to perform the time integration to update the variables. This is the first order in time, but we have higher order, like the Runge-Kutta methods in second and third order. And then we check for output, and then we just keep on repeating unless we reach the intended time for the solution. So now I'll just show you some of the applications of this. For example, this simulation. So this is again going back to the simulations of jets evolving through a gas distribution inside a galaxy. This is a setup for, this is a 3D simulation. I'm showing you a slice. The scales on the X and Y axis are in kiloparsecs. You can see some distribution of matter over here. So this is density, log of the density. And I'm showing you a slice to the box in the 3D. So we initially set up a turbulent gas distribution. We let it evolve for some time. We let it thermalize, and it forms this nice turbulent filamentary structures. And then we let the jets go through. We have done the simulations for several different parameters, and each of the simulations are quite expensive, almost each of them almost like 1 million CPU hours. This kind of simulations are also extremely parallelizable because the Pluto scales very well. So sometimes we run them on 2,000 to 3,000 processors at a time. And so these are the whole list of simulations we've done. The good thing I wanted to impress upon you is this. Since these are small scale simulations as opposed to the cosmological simulations where a single simulation is extremely large itself, but here, for example, this is 1/20th of the time. One simulation takes 1 million CPU hours compared to a cosmological simulation that takes 20 million CPU hours. We can perform a parameter estimate. We can change the power of the jet. We can change the density distribution inside the galaxy, and then see how things evolve and see what are the dependence of different parameters. So I'll just show you this movie. So you can see the jet is strongly, so this is density, this is temperature, and this is pressure. So first, let's look at the density movie. You can see the jet is strongly interacting with this dense medium. It is trying hard to push these clouds aside and go out. You can also see these clouds, which are quite far from the axis of the jet. So that jet is at 0 with a width of about 100 parsec. But these clouds are about 1 kiloparsec away. almost 100 times larger than the size of the jet itself, they are also getting affected. You can see from the temperature plot, all of this matter inside is getting hot. And this is the pressure. So what I really wanted to highlight in this here, you can see there are some conical structures being formed. And these are called Recollimation shocks. And these are often observed in extragalactic observations where you see knots in the jet structure. What's happening is that the jet is, as we inject the jet, it is trying to expand on the sides. But then as it's expanding, there's a back reaction from the external environment, and then it starts to fold back in. And you form these conical shocks, and this keep on repeating. These are called Recollimation shocks. So these are some of the things that we study here. For example, another thing is we inject jets of 2 different powers. The more powerful jet just punches through and goes away. But the less powerful jet takes a really long time, and these are called frustrated jets. And these are observed in systems where the jets are really confined in the central regions. And what we find, at least in our study, is the frustrated jets or the trapped jets are also important because they also shock a large volume of the galaxy. Then we have jets, for example, at different in a disk-like system where there is a gas disk, and jets of different orientations interact differently with the density distribution around them. For example, the vertical jet quickly escapes out, whereas the inclined jets remain trapped inside the disk for a much longer time. Okay. And what is important is not just to make the simulations to understand the dynamics and make nice movies. We also need to understand what is the physics that is going behind them. So one of the important aspects of this is also to predict something from the observations and try to compare with the observations. And this is something, again, one of my students, Meenakshi, is working on, trying to understand the different observational aspects of the jet. One of the results, for example, we have was predicting the emission from the shock gas, or the morphology of the emission of the shock gas. I'm highlighting this particular case where the jet is inclined inside the gas disk, and almost all of the disk is shocked. But when we try to compute the velocity dispersion or the width of the O3 lines, or the oxygen 3 lines, we find the highest widths are in regions perpendicular to the jet. This was a bit of a surprise initially, but then in observations we also see that where this black contours are the jet, and the galaxy disk, you have to take my word for it, they don't have the contours here, is along the jet. But the highest velocity dispersion you can see is almost like a funnel above and below the jet. And what's happening here is the jet is confined, it's stopping as it's going outwards. But then it's like a chimney, it's escaping through the minor axis. So this is the major axis of the galaxy, and this is the minor axis. So all the trapped jet material starts escaping out like a chimney. And this causes more outflows in the vertical direction and not just along the direction of the jet. And that's what we can predict. So this kind of work where you try to predict something which can then be tested with observations is very vital to confirm whether the models that you're doing are at all correct or not. Again, another question that we have, just go to the next phase, is the effect of star formation rate. So I'll just show you a movie of 2 galaxies interacting and colliding with one another. So this was a simulation that's quite old now, but this simulation is very spectacular, and I'm sure you must have seen it at different places. So 2 galaxies are merging, and then something will happen right now. You can see there's a big explosion that happens. So what's happening here is these 2 galaxies start to interact. Maybe I'll just play the movie once again. Oops, sorry. So 2 galaxies, they all have a central supermassive black hole and also have gas inside them. As the galaxies merge, the black holes also merge, and all the gas that was there in the galaxies all come together in the central region. And it accretes onto the black hole and causes this outburst, either in the form of jets or winds. This is not really resolved in this particular simulation. So what was previously thought was all of this outflow will just kick out all of this gas. If you just see how the gas was being thrown out from the system, you can see that there was this massive explosion, and it throws out all of the gas. So this is how people had conjectured that the black holes will control the mass budget by that when they activate, they throw out all of the gas, and then the galaxy stops forming stars because it doesn't have any fuel to form stars. So from our simulations, we are finding that it is very difficult for the jets actually, once you start resolving the structures, to throw out all of the gas. So again, this is a very important thing to understand. This simulation that I showed you was in 2005. That was a state-of-the-art simulation at that time. But now in present age, as we have more powerful computers, we can run the simulation at much higher resolution. And if you increase the resolution, what you find is this interaction between the jets and the gas or all around it becomes very difficult. It's very difficult to throw out all of the gas in the galaxy and stop stars. So this is one of the powers of some of the improvement of the growth of the HPC, that we are starting to find out new results that was sort of hidden because of lack of resolution in the previous years. So again, but we have to come back to the idea of how the galaxy of these jets and outflows affect the star formation rate. And this is again one of my students, PhD student Ankush Mandal, is looking at, where we then Ankush has devised a new algorithm to identify dense regions inside the gas disk. It's called a clump finder. And inside one contiguous cloud, then we can perform the statistics to understand what is the turbulence, and then using some prescription of subgrid prescription of formation of stars, we can predict how much of stars can form. So some of the early results from this is the galaxy, as the jets interact with the gas distribution, it increases the turbulence. Now, why am I talking about turbulence? Because if you just look at an individual star forming region where the gas cloud is collapsing due to this internal self-gravity, if you have nothing to prevent it, it will all go inside and form the star. It will all collapse. However, if you inject a lot of kinetic energy and random kinetic energy inside the system, so that adds an added pressure that prevents the gravitational collapse. So in star forming regions, there's always an interplay between the outward push or a outward support given by the turbulent pressure distribution and the inward collapsing nature of the gravitational forces. So in this kind of violent systems where the jets and winds are strongly interacting, what Ankush finds is overall, you can induce enough turbulence to reduce the star formation rate, which is what you can see in the top plot, where the gray line is a control simulation without any jet, but all the other lines with the jet at different sort of parameters at different inclinations in this particular case are lower in star formation rate by a few times. So you can indeed affect a larger volume and lower the star formation rate momentarily, at least for a few mega years, by injecting more turbulence. But you can also see this is the star formation rate surface density just at the edges of this region. So there's an evacuated region here because the jet has really kicked out everything in the central 1 kiloparsec. But at some locations, you have very high star formation rates. What's happening here is a jet is actually compressing the gas due to shocks. And this compressed gas has a shorter free fall time. I showed the free fall time earlier. Here, the free fall time is inversely proportional to the square root of density. So with shorter free fall times, these are forming stars at a higher rate. So both these kind of things can take place, where the turbulence can lower the star formation rate, but compression can increase the star formation rate. And this kind of things you cannot do unless you're resolving this individual gas structures. So more resolving power is essential to understand new physics that may appear in these systems. So in the last 10 minutes, I'm just going to highlight again a new scheme that we are developing as a part of an application of the relativistic magneto hydrodynamic simulations of jets. Again, what is it? The main driving motivation for this was to better predict synchrotron emission. So synchrotron emission is when you have relativistic electrons gyrating along the magnetic field lines, and that gives out emission because of the moving charge particle, accelerating charge particles. And if those charge particles are relativistic, you have something called a synchrotron emission. What is important in the synchrotron emission is what is the phase space distribution or the energy distribution of these relativistic charge particles. Now, I talked about the jets. I did not really talk about the composition of the jets. It is theorized that initially when the jets are launched, they are made up of electron-positron pairs. So they are mostly leptonic charge particles. But as the jets are evolving, they drag matter along with them. And there is some dilution of this leptonic with some hadronic component that gets dragged in. And you can have a mixed jet. But essentially, the synchrotron emission is given by the leptonic components. And what is important for us, so this is the emissivity of the synchrotron emission. It depends on the orientation of your line of sight with the magnetic field. So N is the directional line of sight, and B is the magnetic field. And then it depends on the integral of this function, where Ne gives you the energy distribution of the charged particles that are giving the synchrotron emission. So in normal simulations so far, people have just assumed some power law distribution of electrons, but in a new update, what we have coupled is a particle plus fluid approach. So what we do is we launch particles, which are like collection of a bunch of relativistic electrons along with the flow of the jet. And each particle then has a spectrum and energy distribution, and we inject many such particles. So the particles move along with the jet. We evolve the phase space evolution of this particle, of the energy distribution of these particles, for example, through this equation. So these are, I'm just condensing a lot of material in a very short time just to give you a flavor of what is being done by advancing this field. So essentially, we consider these particles as a collection of particles that represents individual distribution of relativistic electrons that are advected with the jet flow. And for each particle, we solve their phase-space distribution to understand the evolution of their energy spectrum. But that is not all. These particles, we can launch them with some energy distribution, of course. But then at shocks, if the particles encounter shocks inside the jets, if you remember, I talked about the Recollimation shocks, where the jets expand and then come back again. So if it goes through such shocks and other places, they can get accelerated. So this is called particle acceleration. And this is, for example, we have encoded in our setup, and this is called the Fermi-1 acceleration, where we distinguish whether the particles are crossing a shock, what kind of shock it is, whether the magnetic field in the local region is parallel to the shock front or perpendicular to the shock front. And depending on that, the particle spectrum will be different. This all comes from, again, a different class of simulations called particle in cell simulations, where they just resolve an individual shock structure to identify what is the efficiency of particle acceleration. But what we have done is we have taken those results and put them as a subgrid prescription in our code. So we cannot resolve individual shock and gyro radius of the particles, but we just identify shocks, we identify the strength of the shocks, and using the subgrid prescription can apply and say how much of the acceleration the particles will face. And all of this is encoded. So we have done, again, a range of simulations of different jet powers with more realistic setup of the ambient environment and the jet injection. And I just wanted to highlight this last line. These are some of the state-of-the-art simulations right now, because this kind of work is really not being done in other facets. So at the end of the simulation, we almost have 20 million particles inside the system along with the jet flow. And that is why this kind of simulations becomes extremely expensive. So each of the simulation, again, is almost like 1 to 1.5 million CPU hours with just modest sizes of the jet. So I'll show you one of the results. So again, these are 3D simulations. I'm showing you a slice. On the left-hand side panel is the density. You can see, so now I don't have the clouds yet, because we are just evolving the systems. So you can see that the jet evolving into a conical structure. The injection is from the center. You can, if you look close enough, you can still see these Recollimation shocks. Now I'm plotting the same density on the right-hand side panel, but in a black and white contour. But what I'm plotting in color is the maximum energy of the particles. So if you look closely, you can see that inside the jet, everything is yellow, which means so this is log of the Lorentz factor distribution. So the particle energy is gamma mc square, because it's a relativistic particles, MEC square, electronic mass. So this gamma essentially gives you the energy of the average electron, let's say, or the energy of the largest electron in that particular particle. So you can see inside the jet axis at this particular sites, for example, there are strong bands of yellow. And these sites really match with the sites of Recollimation shocks. So first of all, we can reconfirm that at Recollimation shocks, particle acceleration does take place. And then as the jets go in, the particles reach the top of the jet. There is a strong shock here. The particles get shocked. And then as they are coming down, they cool down, they lose energy because they are emitting synchrotron radiation. Because of this radiative losses, they also lose the energy. What is really interesting about this is now with this hybrid scheme of particles plus fluid, we can track the evolution of the particles and see in complex cases where you have a lot of turbulence inside, how the trajectory looks like. For example, if you focus on this particular particle, it went up there, made a loop, exited the jet, but then made a loop and then was close to the jet and was picked up by the jet flow again, and then went up again a few kiloparsecs, and then finally came out of the jet. Similarly, this particle, it goes up, it exits the jet because it hits the shock, this stop shock. But then somehow it gets dragged back in, and then it forms this extremely weird loop and then goes back. So in complex situations where you have a lot of turbulence inside the jet cocoon because things are interacting non-linearly, you cannot really apply a simple homogeneous picture to predict the evolution of the particles, as has been done in semi-analytical calculations. So this is another power of the simulations, where we can start to identify these complex evolutions, which we otherwise would not be able to do. Again, I just wanted to highlight a particular kind of simulation. So this jet is showing something called a kink instability. So this is a MHD instability where if you have toroidal magnetic fields or helical magnetic fields in a jet, the jet will start to bend. You can see the jet is bending over here. So this is again a 2D slice. The 3D volume rendering looks like this. The top of the jet bends. And this will have interesting implications of if you observe the acceleration side, because as you can understand, as the jet bends, it will start shocking all these regions, and each shock will also accelerate particles. So if you look at this, for example, that's a prediction of the simulations. If you look at the U band, you can see an extended tail like this. Sorry about that. I think I'm almost near the end of my time, so I'll just quickly rush through these last two slides. So what I'm showing here is the evolution of the spectrum of particle. Just to give you a flavor of what happens. So initially we have a power law spectrum. The spectrum changes because of the decay due to radiative losses. So the standard spectrum, just forget the movie for now. The standard spectrum would have been expected to be something like this, where you have a sharp exponential decay in the particle energy, but a power law in the lower energies. And this is the standard expected result from a decay. And this is what people have used in standard analytical calculations. But now if we have the simulations with complex interaction of the particles and they undergo many, many shocks in their trajectories, the final spectrum looks completely different. This is in log space, and this looks like a parabola in the log space instead of a power law with exponential cutoff. So this begs us to rethink how we can model the spectrum of such particles. And this again would not have been possible if we had not done more resolved simulations where the particles are interacting with the shocks and things like that. So I'll skip this slide and go to my summary slide. What I try to show you is that the jets, so just to summarize the main scientific results, the jets strongly affect the gas distribution inside the host galaxy. And next generation telescopes, as well as more cutting edge simulations are needed to identify or resolve structures to find how these outflows are dumping energy at different scales and how they feed back into the whole story of the galaxy evolution. Then I briefly showed you a new hybrid model where we evolve cosmic ray electrons, these particles as I'm saying, or the cosmic ray electrons along with the jet. And in their synergy, we try to find out how the particle spectrum changes. And this particle spectrum will also then affect the observed emission processes. And I just wanted to highlight this particular slide that, for example, upcoming telescopes such as SKA as well as NGVLA. NGVLA is not really talked about in this conference much in this workshop, but this kind of large-scale telescopes will really usher a new window where we can try to resolve structures. And this was a nice simulation that was done by Christina in 2018. And where we can try to understand how these jets are interacting with the central regions, because for now, all of this will appear just as a blob if you look at with the modern telescope, because the galaxy is far away. But with upcoming telescopes, we will be able to get more insights into the internal structures And that's why we also need more such simulations to also understand what we see in the observations. So I'll end my discussion here. Thank you.
Thanks, Dipanjan, for a very interesting talk, very interesting results. So yeah, I can see, I mean, even I had a few questions, but I will catch you later. So
Sure.
Let's go by the hands. Shumit Banerjee, please unmute yourself and ask your question.
Thank you, Dipanjan sir. Good morning.
Good morning.
And yeah, for the lovely presentation. I have a question regarding the very first animation that we saw in your presentation on the explosions that we saw when the galaxies were forming.
Yes.
So my question is, are the explosions the same phenomena as we see in the stellar nova, or is it something different in those cases?
No, so this explosion, as I said, these are driven by the supermassive black holes. So these are very similar to the kinds of jets and outflows that I was talking about later on. But the thing is, this explosion looks almost like a spherical outburst. Whereas if I have shown you the jet simulation, they look at conical outflow. This is because they cannot really resolve the evolution of the jets as such. But if I play the movie and go to the center to highlight the explosions. So for example, this one that's happening. So what's happening here is in this particular large-scale simulations, what they do is near the supermassive. So first of all, the resolutions of the simulations is about a kiloparsec or 300 parsec in this particular case. And the black hole is 10⁻⁻⁴ parsecs. So you can see that they can't really resolve the central regions. What they do is they dump a lot of energy, assuming that the black hole has given out that energy in a spherical region around the central black hole, around the maximum resolution that they can afford. And that is why they look like a big evolving bubble, but these are driven by the supermassive black hole.
Okay,
thank you. Yeah. Abhishek, please go ahead.
Thank you, sir, for this talk. My question is related to the jet simulation from a black hole. So whenever a fast jet is moving along the mass of galaxy, is there any possibility to have cavitation bubble, present of cavitation bubble or cavitation explosion from it?
Cavitation explosion. So this is something that I have not really thought about. So I can't really give you a ready answer for this. So I'll tell you what we see actually in our cases. We see that as a jet is going through, it strongly interacts with the gas. So the interaction becomes completely nonlinear. Cavitation may happen when you have a rapid expansion, let's say, something. But what happens in this jet is you have a strong magnetic, or not a strong magnetic field, but a magnetic field that keeps the jet also confined. And they remain very narrow, and also they have a strong high momentum because of their relativistic jets with the Lorentz factors of 2, 3, even up to a few tens of kiloparsec. So they remain very strong and collimate. They're almost like a strong jet that will punch through something. So before the cavitation happens, the jet will just go through. But I have not explored this in great detail, to be honest.
Okay, sir. Thank you, sir.
Rohit Nair, please go ahead.
Am I audible, sir?
Yes, please go ahead.
It was a very wonderful talk and I liked it. I have a general question on black hole jets. Can black hole jets change the thermodynamic nature of a star cluster where stars are still active, young, and formation is still going on?
Can black hole jets change the thermodynamic nature of star clusters? If the black hole jets are interacting with the star cluster, there is a possibility that they can change the thermodynamics of the gas distribution of the stars. First of all, let me tell you that the stars, once they are formed, they will not be affected too much by the black hole jets because the black hole jets are really very low in density. Okay, so they really affect the tenuous gas distribution that we have in the galaxy. The star will almost see like a solid object embedded inside jet. And there are models where people consider this outflows driven by the star add mass to the jet. So if you remember, I talked about this leptonic jets and they gain some hadronic component. They say that some people have theorized that it is this mass lost by the stars that is also contributing to the hadronic component. But for the thermodynamics of the star cluster, you will need to say change in some the dynamical nature of the star cluster. So that can happen in some way if you also change the gas distribution, which will back react on the star cluster. But I don't think it will change too much the thermodynamics of, or the dynamics of the star cluster itself.
Okay, thank you.
Okay, we can go to the next question. Sri Vishnu S, can you unmute yourself and ask?
Hi, Professor Dipanjan. I'm audible, right?
Yes.
Yes, you are. Please. Yeah, please go ahead.
So I have a two-part question. First is regarding to the formation of supermassive black hole. Is it similar to how it's like formation of a protostar and then formation of a main sequence? Is it similar to that hierarchy, or can it?
So Vishnu, your voice is breaking.
that?
I'm not able to hear you very clearly.
So yeah, same here. So Sri Vishnu, if maybe what you can do is you can try to type it on the chat box if you can, or send it via email, and
But
we
the
will
chat
try
is not
to
open, I think.
Okay. So then probably you can try speaking once more. If it doesn't work, I will request you to send the question via email. Sri Vishnu, you want to try once more? Okay, we can come. Yeah. Yeah,
Audible,
please.
right? Yeah. Okay. Sorry about that. So I have a two-part question, which first in regarding to the formation of a supermassive black hole.
Okay.
So what I want to know is that are they similar to how a stellar black hole is formed, as in it's like a protostar, and then next the main sequence, and next is the supergiant. Are they similar to that formation, or can it be directly formed from molecular clouds, as in similar to a protostar? And then the second question is that regarding the illustrious simulation. So these simulations are confined to a cube, as in like 50 megaparsecs and 100 and 300 megaparsecs. So what I want to know is that since it's an n-body simulation, wherein the Big Bang is treated as a point particle, can we evolve the simulation, as in say from 0 megaparsecs to as in hundreds or thousands of megaparsecs, wherein the simulations run for more number of years, so that can we identify any new physics which we couldn't directly? So yeah, thank you.
Okay, so I'll answer the first part of the question first, and then try to attempt to answer the second part of the question, although I think Tirth may be the best person to answer that. So the first part of the question, you have asked a very difficult question. This is something that is not really known, how the supermassive black holes are formed. So the current understanding, so as well as from now, from the LIGO observations, we know that there are really large masses of black holes that are being formed, hundreds of solar masses and thousands of solar masses. We do not know exactly how these masses of 10^6 solar masses will be formed. So the current understanding is, so this is not a confirmed thing. We are still working on things and trying to understand through observations and simulations as well. Current understanding, in the early phase of the formation of simulation, we can have a direct collapse to form this intermediate mass of black holes, intermediate masses of 10^4, something like that. Even lower masses, 1,000 solar mass black holes by direct collapse. And there are several papers. If you are interested, I'll ask you to look up the papers. Martha Bolanteri and her postdocs and students who have been pursuing this field of line of investigation. But there are several several caveats to this as well, because how do you collapse things? There are several tuned conditions to the molecular gas conditions as well, which are debated in the literature, but you can form this direct collapse. The other then is, once you have these direct collapses, if they form in nearby vicinities, you have mergers, and then there is a hierarchical growth of the black hole. So to form this large-scale supermassive black holes that we see now, they must have gone through a hierarchical evolution by growth and merger. But it's not always the case that it's simply mergers that drive the growth of the black hole. Again, there was a nice review by Martha Bolentari again, where they showed it's just a secular evolution by gas accretion of the black hole can also lift up the mass to a few million solar masses after you start from a basic seed mass of 10 power 5, 10 power 4 solar masses. So there are these two mechanisms. Either you accrete mass and then you keep growing the mass of the black hole, or you have mergers. But how you form the first black holes, so the first intermediate mass black holes, is through direct collapse. And that is the current understanding. The second point, why don't we take thousands of megaparsecs? So of course we would want to expand these boxes, because essentially what we are limited by is how far is the Hubble radius that we can see, because we are going beyond that doesn't really make sense. But we also want to include larger boxes, because as you go to larger boxes, you can also form larger structures. You can also form larger clusters. So your statistics of the large scale structures and large scale clusters will also improve. The real limitation is the resolution and how much of compute time and compute power you can put there. So I think that is what is limiting our large scale boxes right now, and people have also started moving away from large scale boxes to smaller scale boxes, but more resolution. So Illustris again is one of the flagship simulations. They have the one I showed is the original Illustris, and now they have Illustris 50, where they have slightly reduced the box size, but they have increased the resolution. So we would want to go in both directions, ideally, as we improve in compute power.
Okay, let's see. Shukalpa Kundu, please go ahead.
Yes, sir. I have a question. Are these simulations baryon only, or dark matter components are also present?
Now, for the fluid simulations, they are just so by baryonic and dark matter. Let me confirm that I am considering only the gas. When people talk of baryonic and dark matter component, they usually refer to the stars as baryonic component, and the dark matter is the dark matter. But for my simulations, the distribution of stars is all in the background. The baryonic component I have is just from the gas in the system. From the large scale simulation that I showed, it has everything. It has gas, stars, as well as dark matter.
Okay, thank you.
Rajesh Chandran, please go ahead.
Good morning, sir.
Good morning.
Sir, my question is based on the artificial monopoles which you have been talking during the flux density and magnetic field, sir.
Yes.
Sir, will the artificial monopoles will it give the better accuracy in the results when it when we take a concurrence with respect to the flux density and magnetic field, sir?
I didn't really understand your question. So, for example, firstly, artificial monopoles are not correct. So we would want to get rid of artificial monopoles from our system, either by designing the scheme so that they're never produced in the first place, or as I showed you, how by removing from the system. So we don't want artificial monopoles at all in our system, right? Because it is completely unphysical and does not obey the Maxwell's equation.
So which means like there is no point in looking into that area rather than getting into the natural aspect of dipoles only, right, sir?
That's right. That's right. Exactly.
Thank you, sir. Thanks for a wonderful talk, sir.
Thank you.
Okay, our next question is from someone who shows up as live CID something. So I don't have your name, but if you know who you are, please go ahead and ask the question. Okay, live CID. Okay, we will come back to you if time permits. Tejas Joshi, please go ahead.
Sir, am I audible?
Yes, please go ahead.
I had two questions. My naive understanding of turbulence is that it acts as an energy dissipation mechanism at various scales. So do you suspect that the turbulence induced by the jets contributes to the star formation process?
Okay, you have asked a very pertinent question. So the basic theory of turbulence is that you're cascading energy into different scales, but this energy will stop at some scale where the energy is dissipated and converted into thermal energy. Okay, so but before it is dissipated, so the dissipation scale is much small. So before it's dissipated, it adds to the total kinetic energy budget of the system. So the way the jets affect the star formation rate is by increasing the kinetic energy budget at spatial scales away from the dissipation scale. Okay, so then what happens is a test particle, for example, would try to collapse, but due to turbulence, it will not fall in, but will be moving at different directions. You can think of it in this way. So this is how the jets or any other, say, for example, supernovae-driven turbulence as well, will contribute to adding the turbulence. So why are jets more important? Because they have more energy and momentum than supernovae, so they can induce a lot more turbulence in the system, jets or any other black hole-driven outflows. So that is how the jets are expected to affect the star formation rates by affecting the turbulence. There is another thing that I told you. So jets reducing or making the star formation rate inefficient, that is called negative feedback, because it's a negative effect on the star formation. Other is the jets directly go and hit a gas cloud and then compress the gas cloud due to its momentum. And if this gas cloud is also radiating, it forms a radiative shock where the density can increase by several orders of magnitude. In that case, what happens is that the density, since it increases, it can be more prone to collapse. Although the turbulence is also increasing, if the increase in density is higher than the effect of increase in turbulence, it can collapse much faster and form stars. So that's one called a positive feedback. So jets can do both, positive and negative. How it does both, which is more dominant, depends on the parameter of the system, whether the jet is more powerful, whether the gas distribution is less dense, how much of the jet is being coupled to the system, and that is all. So it goes to the nitty-gritty details.
Sir, I had another question. Why does the divergence B problem occur? I suppose it might take too much time to explain, but since the equations we started with are consistent, I would suspect that divergence of B should not be a problem by itself, but it seems to be a consistent problem all over the place.
Yes, it occurs because of the fact that we are discretizing a continuous magnetic field. It is these discretization errors that start to grow. So we start off with the error at the machine scale, but then it will start growing. And this after a few times, it will screw up your system. So that is why it's mostly because of the fact that we are trying to represent a continuous system on a discretized grid.
Thank you, sir. Thank you for a wonderful talk.
Okay, Shubham Bharadwaj, please go ahead.
Audible, sir?
Yes, please go ahead.
So my question is regarding, sir. So around the supermassive black hole, there are accretion disks and there is tidal disruption events also happen. So are these relativistic jets and tidal disruption events are interlinked to each other? Like, do they affect each other, or in what scale do they affect each other?
So a TDE can can give rise to a jet, because as due to a TDE you can form an accretion profile that will give rise to a jet. What you're asking is if a TDE happens when the jet is active.
Yeah.
It will cause fluctuation in the properties of the jet. It will cause a momentary spike in the jet luminosity because you are adding more matter, and you can have a momentary increase in the flux of the power output of the jet.
So, sir, follow-up question. So, when you are like simulating these jet structures, as you have shown in your talk, so are you considering the TD's effect in this?
No,
or not?
We don't have TDs yet, because for the simulations I have performed, we just assume that the jet has been launched somewhere outside our grid, because we are not really resolving the jet launching scale in our simulations. So we just assume a constant flux of relativistic energy and momentum in our system. But when people do simulations of actual formation of jets, if you look at this paper, the latest cutting-edge simulations where they form these jets from GRMEC simulations, you'll find that the accretion disk is all over the place. There are tearing modes that break up the accretion disk, and they almost look like a TDE event.
Thank you. Thank you. Thank you.
Okay, Mohit Pawar, please go ahead.
Basic question. what are the initial conditions in the simulation code that you have used to generate the galaxy distribution, and how sensitive these conditions regarding the galaxy distribution?
Regarding the galaxy distribution, so for our case, the galaxy distribution just serves as a background source of the gravitational force. Okay, so we assume a distribution of the stellar profile and a distribution of the dark matter profile that gives you an external gravitational field, or which acts on the gas in our system. So for some of the works, we have used a double isothermal potential for the for the stars and the dark matter. For another work, we have used a standard profile of the dark matter using NFW and others. So I'll refer you to my papers from Mukherjee 2020 and Mukherjee 2016 if you want to know more about how we've set up things. We have not set up a galaxy for the large scale problem that I showed. For the gas distribution, what we assume is a hydrostatic distribution in terms of pressure. But the gas clouds are included by performing some sort of a random distribution of clouds with such that it has some properties. It has a log normal distribution in the density space, and it also has a power law distribution for a 2-point correlation. Again, I'll refer you to all the technical details. I'll refer you to my paper in 2016 and 2020 for details.
Okay. Thank you, sir. Thank you, sir.
Very good. We'll take a couple of more questions if possible. So again, there is a username live CIDF4F7 for something. There's no name there. So if you know who you are, please ask the question. Maybe, okay, we can't communicate with them. Shomik Mitra, please go ahead.
Hello.
Yes.
Okay, sir, you have shown in one slide where you have shown the MHD equation. There you have shown the fluid magnetic field, I mean magnetic field in fluid frame. There you have shown the 4 components. One is B0 and another is B vector.
Yes.
So B vector, that is fine. That is, we know that the 3 component vectors.
Yes.
But what is the significance of B0?
So B0 is, we are writing the magnetic field vector in a covariant form, so that we can represent them in covariant products. So to understand this, I will refer you to this paper so if I just flash the slide, just give me 1 second. Yeah, so you mean this small b, right?
Yes.
So this is the covariant way of writing the magnetic field. Essentially, you don't have a covariant vector, but so it's easier to represent the MHD equations in this covariant form. And essentially, if you go to the rest frame of the fluid, it's also easy to understand if you look at this covariant electric field. I'll refer you to these papers of Mignon in 2009 and Mignon in 2019. So 2009 gives you it's a numerical paper, but it gives you the equations that are being solved initially. And 2019, so this is for the main numerical paper for relativistic MHD. That gives the numerical scheme, but the first sections give you the equations. Mignon 2019 is a paper that derives the set of equations for relativistic resistive MHD, where now you do not assume that the electric field is 0 in the rest frame because it's a resistive MHD. And if you look at this paper, all of these are derived in more detail, but also the fundamental book is Annulate 1990.
Sir, I mean, so this is, I am quite familiar with this, but I just want to ask, like, is there any physical meaning of B0? Like, B vector, we know that magnetic field has 3 components. Physical
meaning of B0, to understand that, we have to understand where it comes when you do the derivatives of the stress tensors, right? So okay. Physical meaning is a bit lost in the mathematical formulation of things. It's just a way of writing the when you get the components by taking the conservative form of the derivatives of the stress tensor, what do you get out of it, and then writing them in this form is much easier and simpler to understand.
Okay, sir, one follow-up question about the simulations. Like, if we are doing normal MHD equations, we are only dealing in 3 frame. I mean, X, Y, Z. Now, let's say if we are using the general relativity or relativistic frame, we have now 1 plus 3, right? So the dimension. So, but we know that we cannot solve the vacuum equation. So we need to supply some floor values of density, pressure, and all these things. So how do we determine that floor value?
That's a very important question you've asked us, and this is something that we push under the carpet. The floor value is completely undetermined. So if you look at any of these large-scale GRM simulations that launch jets and stuff, the floor value is just determined by the machine precision. Okay. So they usually the typical values that we put in are 10 power minus 12 or so. That is far lower than any of the standard values you get. Ideally, of course, that is not correct because that will be determined by other processes. For example, for the Blanford's-Knight process, the low density phase would be defined by the charge cascade and the Goldreich-Julian densities essentially. But this is not really considered in the simulations. Prayush Kumar will give a more updated talk on GRMHD simulations and where they also evolve the metric. Maybe you can get some insights from there as well.
Okay, sir. Thank you.
Okay, so our last question of the session, Asha Lakshmi, please go ahead. Asha Lakshmi, can you unmute yourself and ask the question? Okay, if not, I think this is a good time to wrap up the session. So let me thank Dipanjan again for a very interesting talk and such a stimulating discussion session. And what we'll do is we'll have a break now and we'll come back at 12 for the next talk. So see you in kind of half an hour.
Thanks, Steve. See you.